Tell us today about Siegel Veech transforms are in L2.
All right, how many takes do I get? So it's great to be back, and I am actually still technically an adjunct faculty member in the department, so it's good to be home. So what I'm going to tell you about today is joint work with Yitwah Cheung and Howie Mazer, and then if we have some time in the middle, I may mention some joint work with my current PhD student, Samantha Fairchild. So I want to start, since I know not everybody in the room works with translation surfaces. I want to start by telling people what a translation surface is and what the particular set. So what we're going to do is we're going to look at sets of points in the plane, and we're going to try and average things over sets of points in the plane. Now, this is a very vague description. Let me tell you where these sets come from. So they're going to come from translation surfaces. So if you see, a word, kind of a descriptive word that describes a kind of transformation, and then you see kind of a dimension of a manifold, what this usually means is you have your manifold, you have some atlas of charts where the transition maps are this. And so that's exactly what these things are. But I'm going to give you a slightly different definition and then show how to get to, I'm going to draw you a picture and then tell you about what the definition is. So the picture is, well, here's a translation surface. It's a square or a rectangle with opposite sides glued by translation. So this, of course, gives me a nice flat torus. And every point on this flat torus kind of looks the same. But maybe I'll just mark this point just to sort of keep an eye on it. So I'm going to mark that point. But that point doesn't really actually look any different. It still has angle 2 pi around it. However, if I were to do this with instead something, let me just cut out a little square from here. And now let me do the following gluing. So this is not part of it. Okay, so this is not part of it. I'm just going to draw it in here. And now I'm going to glue opposite sides of this thing by translation. And now there are 8 sides. They're paired in 4s. There's 4 pairs. And notice that if I include this square, I would get my torus with this square as not part of it. And the square would be have sides, I guess, 1 and 2, with 1 and 2 glued to each other. And from that, I get, that creates a little more genus. But now there is a point that really does genuinely look different from every other point. Right? This point has angle 3 pi over 2. These 4 points all have angle 3 pi over 2 in the torus. And when I glue them together, I get this point. And I actually drew that with the correct number of things. Each of these is supposed to be a pi. So this has total angle 6 pi at that point. So from an analytic perspective, how I want to describe this is, well, think of this thing as living. Think of this whole board as the complex plane. I've taken something in the complex plane. I've taken a domain, and I've glued things using holomorphic maps, right? Just z goes to z plus c. So I have a Riemann surface structure. And you might say, well, what's going on over here? Well, if you have a Riemann surface structure on a punctured object, you can fill it in. That's, go back to complex analysis class, and that's I can't do the exercise, but you can. And so you had a Riemann surface structure, but you get more than that because you also have the one form dz living here, right? You have graph paper on the complex plane. So you can just integrate, you can look at dz, and what you get is you get a holomorphic one form. So what I think of this thing as is it's a pair x omega, where x is a Riemann surface and omega is a holomorphic one form on x. Now, suppose you have something like this, a Riemann surface and a holomorphic one form, and you want to go back to a picture like this, or at least get a kind of an atlas of charts to the complex plane. Well, here's how you would do that. Here, maybe I have several zeros here. Maybe it's a genus 3 surface, and I have several zeros. Away from the zeros, what I'm going to do is I'm going to take a point P0, and here's my chart. My map to the complex plane is going to be, so let's say I have a point P here, P. is I'm just going to integrate my one form. And then, of course, in these coordinates, omega is just dz. And that's away from this finite set of points. What happens at this finite set of points, just going back to this picture, I have 3 times 2 pi worth of angle. So near here, the one form looks like d of z cubed, which up to constants is z squared dz. Right? So it's a 0 of order 2 of the holomorphic one form. In general, I have points with I'll have points with a 0 of order k. 0 of order k corresponds to total angle. It's a point with cone angle 2 pi times k plus 1. So k is kind of the excess. It's the excess angle. Okay. So these are the objects I want to look at. And now, so if you don't want to think about complex analytic picture, just think about this picture. Think about polygons where each side has a parallel friend of the same length, and you glue the parallel sides by translation. Okay, so that's what we're looking at. And associated to any x omega, any pair like this, I'm going to associate to this a discrete subset of the plane. How am I going to do this? Well, there's lots and lots of straight lines I can draw on any of these surfaces, right? And if I sort of pick a direction at random and draw a straight line, it'll kind of spread out everywhere in the surface. That's a theorem. But what I'm going to be interested in is straight lines that connect this point to, well, in this case, this point to itself, but more generally, that connect the problematic points. So I'm going to be interested in lines of this form. So maybe this one goes in some crazy fashion, and it's only a straight line when you sort of flatten it out, when you look at it flat. Let me draw a couple of examples here. So here, of course, this is a nice straight line. But so is, let's say you were to go halfway up this side, and then you're here, and then you continue like that, and then you end up here. That's also what we call a saddle connection. So a saddle connection is a geodesic connecting two singular points. And of course, what we want is we want no singular points in the interior, with none in the interior. Here, let me pretend that this is a singular point, even though it isn't. I'm going to mark it. And then what are saddle connections? Saddle connections are things like, well, that's a saddle connection, that horizontal guy. That's a saddle connection, 45 degrees. And if this is the square torus, if you look at the set of saddle connections, and you look at sort of the vector that they give you, right? So you can, given a saddle connection, you can look at how far it went horizontally and how far it went vertically, right? Just keep track of that. Here, the set of saddle connections corresponds to the set of primitive vectors in Z2. So a vector is primitive if its coordinates are relatively prime. The reason you don't get all integer vectors, of course, is if you were to look at, say, 2, 2, 2, 2 is just wrapping around this thing twice instead of going on at once. So what I'm going to define, this set lambda omega, so associated to each saddle connection gamma, if gamma is a saddle connection, I associate to it its holonomy vector, which I call z gamma. Z gamma is just the integral of omega over gamma. So what do you do with one forms? You integrate them on curves. So this is just keeping track of how far you went horizontally and how far you went vertically. So whatever, for instance, if this was, let's say, height 1 and this is length, let's say, some w, then the holonomy of this guy, well, you've gone up 1 and you've gone across w. So it would be 2w plus I would be the holonomy of this guy. Or if this is, so whatever this part is, maybe this is, I don't know, maybe this is w over 2 or something like that. If this is w over 2, let's say, let's pretend it's a very symmetric L, this guy would be w over 2, and the height would be 1, so that would be w over 2 plus I would be the holonomy of this guy over here, and then this thing is that. So this set lambda omega is going to be, it's going to be the set of holonomy vectors of saddle connections. So gamma, a saddle connection on x omega. I'm going to alternate between thinking of this as in C and thinking of this in R2. Okay, this is kind of the picture we go back and forth. Now, first of all, why do you care about this set? Why would anyone care about this set? Well, let me give you the 2-minute motivation from very simple Newtonian mechanics, which is if you play billiards in a polygon, in a Euclidean polygon, billiards in a polygon P, and the angles of P are rational multiples of pi, then if you play billiards in this polygon, you can, each time you hit a side, you can flip over the side. And after you do this, you only get finitely many copies of your original table up to translation. Eventually, you get a translated copy. And so what you can do is from the original billiard table, you can make one of these surfaces, these translation surfaces. And these saddle connections correspond to interesting families of trajectories on your original billiard table. So for instance, if you're interested in what are called generalized diagonals, so a trajectory that starts at one corner and ends in another, they correspond to saddle connections. That's one reason to be interested in saddle connections. They also, for instance, saddle connections are the building blocks. If you want to look at geodesics in the flat metric, so this metric is flat except at this one point where you've squished all of the negative curvature, right? So these are surfaces of negative curvature, except the curvature is concentrated at one point or a finite set of points. And so what a typical geodesic between 2 points on this surface looks like is, let's say I'm a non-singular point. What I'm going to do is I'm going to go to a singular point, turn some amount, more than pi, I have to turn, go to another singular point, turn more than pi, and I'm going to be a union of a bunch of saddle connections, and then eventually I will go to the other point from one of the singular points. So that's what typical geodesics look like. They have to keep visiting this negative curvature set. So they're the building blocks for geodesics, and they arise from billiard trajectories. So now let me define a certain kind of a transform called the Siegel Veech transform. I should mention, actually, I mentioned who this is all joint work with. This is Howie and Yitwah, but this is all of what we're going to talk about is really inspired by work of Bill Veech, who passed away this summer. And so in fact, hopefully, one of the reasons Howie wants to get the paper out is there's going to be a volume in honor of Veech that we're trying to get the paper into. We'll see. I'm going to write this as the Siegel Veech transform, and I'll talk about what Siegel did. Siegel never ever thought about a translation surface, I can assure you that. So this is really, it's the Veech transform, but Veech called it the Siegel transform because it was an analogy, and I'll tell you where the analogy came from in a minute. But the idea is very simple. Start with the function f, which is a bounded, compactly supported function on R2. This is my notation for bounded and compactly supported. So in particular, this includes indicator functions of bounded sets. Given, define f hat of omega. So, this really means of x omega. I'm going to make the x implicit. I'm just going to write the one form to be the sum over all vectors in the, let me write it like z in lambda omega of f of z. Okay. So I just add up the function over all of the saddle connections. Now, that's nice. That's a thing you can do. But I haven't told you, for instance, is there some natural space on which this function is defined, right? There's clearly lots and lots of Riemann surfaces and lots of holomorphic one forms, but we don't necessarily want to look at them all together. We want to look at them kind of organized in some reasonable way. So for that, I need to tell you about what are called strata. So there's this big space, omega g, which is the space of all pairs x omega. X is a Riemann surface of genus G, so it lives in the moduli space of genus G surfaces. And omega is a holomorphic one form. So omega of x here denotes the vector space of holomorphic one forms on x. Again, if this doesn't mean anything to you, don't worry. Just think of a polygon with sides glued. And so that what you get is genus G. It's exactly the same piece of information. But this splits up it's a union of pieces, which we're going to call H of alpha, where alpha is an integer partition of 2g minus 2. So you write alpha as alpha 1 to alpha k, summation alpha I is 2g minus 2. And I want all of the alpha I to be integer, in fact, positive integers. You can also talk about the story where some of them are 0, and this corresponds to having marked points. But if I want this to be a finite decomposition, I don't want to allow zeros for right now. So each of these, this corresponds to kind of fixing the combinatorics, to fixing what the possible angles are. For example, in genus 2, so omega 2 is H of 2 union, disjoint union H of 1, 1. In fact, actually, H of 2 sits in the closure of H of 1, 1. You can slide these two zeros of order 1 together and make a 0 of order 2. We've seen an example of something in here, right? We saw the L in here. Now, I will not attempt to draw this, but if you take a decagon and identify opposite sides, you get something in H of 1, 1. Actually, let me draw a different one in here, which is something I can draw, is if you take, that looks like a torus, but now I'm going to make slits in the torus, and I'm going to glue plus, minus. And then it turns out these points end up being your two singular points. So that's Howey's favorite example in H of 1, 1. OK, so these are the spaces. So I want to think of f hat as going from one of these strata to, let's say, to the reals. But more specifically, I want to restrict to a particular subset of a stratum. I'm telling a slight lie here. The strata, I mean, you can think of them as functions on strata. What really the right thing to do is to think of them as functions on connected components of strata. These guys can have up to 3 connected components. But I'm just going to elide that distinction and say that I'm working with one of the connected components. Now, there's a natural function, let's call it A, from omega g to the non-negative reals, which is just simply the area of x omega, right? So A of x omega is just stands for area of x omega. If you want it in complex analytic terms, it's integral omega wedge omega bar over x. Maybe I need a minus sign. You know what? Now I don't care whether I have a minus sign or not. But the point is, it's just area. It's just you draw your polygons, you look at the area of the polygons. It's, of course, if you scale the whole differential by t, the area will scale by t squared, right? You're scaling everything by t. So so you can always multiply differential by t. But we're going to look at strata. We're going to look at H1, which is the set of area 1 things in a stratum. And because I'm lazy and I don't want to keep writing the 1, we're often just going to write H for that. So H is going to be the subset of area 1 guys. So I'm eliding this distinction. Now, why is this a nice thing to do? Well, one, many of the properties we care about surfaces, we care about one representative, right? We want to nail this down because if I can say something, for instance, for example, about counting saddle connections of length less than or equal to r, on a surface of area 1, I can do it on a surface of area 100, right? I just have to change my r. So this is why you care about area 1 surfaces. Another beautiful thing, and this is a deep and non-trivial theorem independently due to Masur and Veech in the early 80s, is there exists a natural SL2R invariant ergodic finite measure. So I'm going to underline all these important properties. Call it mu mv on H. Okay. So this is called Masur-Veech measure, though in our write-up, Howie has made me call it Lebesgue measure. He won't let me call it Masur-Veech measure in the paper with Howie. So let me just give you one sentence about what this measure is. So remember I drew, for instance, we saw that L up there. This L, what do I need to really specify? Things don't really need to be perpendicular like this. In fact, my drawing kind of makes them not. What I really need is I need these 4 vectors, maybe 1, 2, 3, and this one is independent also, 4. So really, I kind of have my space, H11, is kind of modeled on a R2 to the 4. Of course, there's some of them I have to throw away. It's not all of R2 to the 4, but locally it's modeled on R2 to the 4. And then area is a quadratic form in these coordinates, right? Very clearly, if I scale any of these coordinates if I scale them by t, the whole thing scales by t squared. So I have the picture here is I have this space and I have this kind of area 1 hypersurface. And what I do is I say if I want to know the measure of a subset of the area 1 hypersurface, I take the set of surfaces of area less than or equal to 1, and I take its Lebesgue measure in these coordinates. That's actually what this measure is. Now, I also said something about SL2R invariance. Where was the SL2R action? I hadn't introduced that yet. Well, it's very simple. This sits in the plane. It's vectors in the plane. SL2 hits vectors. So the action is literally on, if you want to think of it in these coordinates, it's literally just acting on each of these R2s linearly. No fraction linear, just honest to God linear action of SL2. So for instance, the diagonal would stretch and contract and so on. And it's pretty clear that area 1 is SL2 invariant. It's also clear from this construction that this measure is SL2 invariant. That's not the hard part, right? Because this is kind of a product of Lebesgue measures on R2, which are SL2 invariant. The hard part is showing that it's finite and that it's ergodic. OK, great. So now we have a measure and we have a function. So obviously, what are we going to do? We're going to integrate this function with respect to this measure. But before we do that, let me actually state the theorem that we prove. And then I want to give you the context and the build-up to it. So the theorem we prove is that if f is in BC of R2, then f hat is in L2 of H with respect to Masur-Veech measure. OK. And something to note, I have a paper with John Chaika where we say that this theorem is not true. We say that if you look at the indicator function of the ball of radius 1, that it's not an L2. Howie pointed out to us that, in fact, the paper with Chaika, so this theorem is with Cheung and Masur, that the proof with John shows that f hat, if you take f to be the indicator function of the ball of radius 1, that it's not an L3. And I'll try and explain that at the end. Basically, it's a measure. We construct a set of surfaces which have way too many saddle connections in the ball of radius 1, and we made a mistake in estimating the measure of that set. We got an exponent wrong. We actually sent an erratum to the journal, and the journal was like, well, does it affect the other results in the paper? I'm like, no. They're like, well, in that case, we're not publishing your erratum. So we put the erratum up on our websites, but it's like, I was a bit surprised. So now, of course, in this paper, we're going to have to say, like many times, like, that thing was wrong, but this thing is right.
Which journal was that?
GAFA. Yeah. I mean, it does not affect the other results of the paper, but it's still, I mean, it's a pretty big mistake. They don't like gaffes. Yeah, exactly. OK, so now let me tell you the context and the history of this theorem and why maybe you should care, or why I care at least. So context. So Veech, when he introduced this, proved the following beautiful thing. He proved that f hat is in L1, that it's integrable, so it has a finite expectation. This you can think of it saying is it has a finite variance, right? And why would you, so Veech not only showed that f hat's in L1, but as a consequence of that, you get the following. So suppose you look at f goes to the integral of f hat d mu. And I'm just going to write mu from now on. So this says start with the function, sum it up over saddle connections, and integrate it over all possible surfaces. Then you get a number, right? This is a number. Everything we've done is linear, right? Everything in sight that we have done is linear. We've added things up, we've integrated, so we've added things up again. So this is this thing is an SL2 invariant linear functional on BC of R2. Right? So you take a bonded compactly supported function, you get a number out of it, it's linear, it's SL2 invariant, which means it has to come from integration against an SL2 invariant measure on R2. There aren't that many of those. There's delta measure at 0, and there's scalar multiples of Lebesgue measure. So what Veech showed, in fact, is that there's a constant so that if you average the number of saddle connections, so for instance, what this says, if you look at the ball of radius 50, and you want to count the number of saddle connections in it for a random translation surface, what you should expect is some constant times the volume of that ball. And these numbers, so Veech actually proved, so this proof works for any measure mu where f hat's in L1. And Veech, in fact, he didn't write it like this, but basically for any SL2 invariant measure, f hat's in L1. And so these numbers see, if let's say tau is some other SL2 invariant measure, there's lots of them. And I'll make a remark, they were sort of classified by Eski and Mirzakhani-Mohammadi in some sense. But these constant C tau are very interesting invariants known as Siegel Veech constants. And they're very closely related to kind of the intrinsic volumes of these spaces. If you normalize the measures on the Lebesgue measure here, you get an actual notion of volume of these spaces. And these numbers turn out to be extremely interesting numbers that turn out often to be rational multiples of powers of pi, which is a whole nother story. But why would people care even about this L1 bound? Well, the answer is counting. People care about this L1 estimate and these L1 formulas because of counting and because of an analogy with the space of lattices. So let me state the counting problem, and then let me go back, and I promised in my abstract some classical geometry of numbers, so I'll deliver on that promise. So counting means, suppose I define n of omega r, here is maybe the simplest counting problem, to be the cardinality of lambda omega intersect the ball of radius r around the origin. So I just count the number of points in the ball of radius r. This is something that naturally shows up for dynamicists, because if you want to study billiards in a polygon, this is like counting special trajectories, generalized diagonals or periodic trajectories of length less than or equal to r. It's a very, very natural thing that shows up. Or if you just want to think about translation surfaces, if you're thinking about the linear flow, these are special trajectories. These are trajectories that don't have typical behavior. And so in dynamics, you either want to understand typical behavior or you want to understand how often atypical behavior occurs. This is kind of a way of understanding how often atypical behavior occurs. So Howie, Masur proved kind of a Chebyshev theorem. He proved there exist constants C1 and C2, positive constants. So no matter what omega so these are constants depending on omega. So he proved upper and lower quadratic bounds. So quadratic, you might kind of vaguely guess this because these are flat and you're counting. If you were to do this for the torus, and you were to count, let's just do the easiest one. Let's count all, not just primitive vectors, but all things. So then you're just counting integer points in the ball, and that's pretty obviously quadratic by standard geometric argument. It's a little more subtle, even if you're looking at just primitive vectors on the torus. That's not an entirely trivial argument. If you're a number theorist, it's one of the things you learn very early on. But you know, it requires a little bit of thought. So just example, right? If I take T2 dz, then if I look at n of this r, n of r for this, then that behaves asymptotically like pi r squared, the area of the ball, divided by zeta of 2. Because this is the probability that a pair of integers is relatively prime. We'll come back to this that coefficient in a second. So Masur proved that. Veech proved kind of an averaged, a consequence of this result is that if you average n of omega r over the whole stratum, then that converges, right? And you divide that by pi r squared, that just converges to this constant, right? Or it's in fact equal to this constant. It's better than converging. It's saying at each scale, if you average, you're actually on the nose equal to something times r squared. But a priori, that doesn't eliminate the possibility that maybe some surfaces are way more and some surfaces are way less. Howie says they can't be way more or way less. But so Veech proved an L1 theorem. And then this is a very brief and kind of potted history of this. Eskin-Mazur proved that for mu almost every omega, n of omega r over pi r squared actually converges to what it is. So there isn't, these fluctuations happen, if they happen at all, if you have things that don't behave like the normal thing, they happen on a set of measures 0. And subsequently, there have been lots of counting results trying to understand, other subsets. So Eskin, Mazur-Schmoll, Eskin, Markloff-Morris. I have some work with Eskin and Zorich, Matt Bainbridge. There's like a whole cottage industry of people proving counting results. But what does L2 tell you about counting? Why does L2 help say anything about counting? Well, what L2 can help you do is at least give you, it can help give you potential information, though we're not there yet. But what we hope it will give us, if we can compute the L2 norm, is estimates on almost everywhere error terms for this counting. So now we have a main term.
Sorry, could you
explain
again how this quantity is defined? So this ball.
The ball of radius r, and then
this is a ball where?
In C, or in R2. Right. So I have this discrete subset. And then I take the ball and I just count. So this is the number of saddle connections of length at most r.
So do you worry about primitive things?
So in general, in a higher genus surface, all saddle connections are primitive, right? You can't just like take a multiple of.
That was part of his definition.
Yeah, right. Yeah, it's
a part of it.
Yeah, it's things that connect something to something else with nothing, one singular point to another with nothing in the interior.
Okay.
In fact, if you try and count things which are just geodesics that connect a pair of points, that grows exponentially. It's a surface of negative curvature after all.
Okay.
So this is the primitive objects are kind of growing quadratically. Okay, so just broadly speaking, suppose the L2 norm, let's say, of the ball of radius r hat. I just want to give you a little bit of. Suppose this the L2 norm of this, maybe the L2 norm squared, let's say, was equal to some function e of r. Okay. Then what could I say? I could say, let's look at the measure of the set of omega such that n of omega r is this chi hat, right? Chi hat, I'm just going to write chi hat r minus what it ought to be, c mu pi r squared. This is the mean of it. I could ask, when is, let's say I want it to be bigger than some, maybe I should have called, let me call this L of r. Let's say I want this to be bigger than, let's look at the probability that worse than some error. E is now some function to be determined. Well, right, I can just put squares on top of everything. Right, so this is the measure of the set of surfaces which have bad behavior. But of course, this is a function minus its expectation squared. And let's pretend that we've normalized mu right now to be a probability measure just for this argument. And so what is this? This is, this is certainly less than or equal to, this is less than or equal to the integral of chi r minus c mu pi r squared divided by e of r squared. Right, this is just your inequality you learn in first year analysis, right? And now this thing, it's the difference between this and its mean quantity squared. So this is the L2 norm minus the L2 norm squared minus the L1 norm squared. Right, so this would just be L of R minus C mu pi r squared quantity squared divided by E of R. So if we could get a handle on what this thing is.
Sorry, E of R squared?
E of R squared, thank you. Yeah. So I mean, this is just I just expanded this out, and I didn't do that step out, right? There's a 2 C mu chi r, and then that gives me, you can all, I mean, this is just in probabilistic notation. Sorry to use E for too many things, right? This is just expectation of E minus expectation of x squared is expectation of x squared minus expectation of x quantity squared, right? That's where E here means something different than it does here. Yeah, here, I'll make this, you know what? This is an error, so it should be a small e. It's a small error. So if we could control what L of R is, if we could understand what L of R is, what this would allow us to do is say, hey, look, the measure of the set of points at time R, which are bad, is small, depending on relationship between L of R and E of R. And then we could use the Borel-Cantelli lemma to get almost everywhere error terms for the counting problem. So that, of course, will rely on us actually being able to compute this L2 norm. Now, I should also mention, in this context of wanting to find error terms in this count, that this has been, there are now error terms which get you a small power savings. And this is recent work of Amos Neveu, René Roer, and Barak Weiss. But they're using methods, so they do get some error terms with the power saving using rates of mixing of the Teichmuller geodesic flow. And it's actually a really beautiful but very technical argument. What we're hoping for is if we can compute this, we'll get a kind of an easy argument. OK, so time-wise, no, I don't want to know how many steps I've walked. OK. So I have 13 minutes, right? So now let me tell you a little bit about where this comes from, and then I'll conclude by saying a little bit about hopes for computing the L2 norm. I guess I'm probably not going to tell you about the proof, though let me actually say one word about that for the experts in the room. The proof is you want to estimate the measure of the set of surfaces which have a lot of saddle connections in the ball of radius 1. So you use what's called the thick-thin decomposition of the surface. You use Khosra. Khosra tells you that the surface can be broken up into pieces, each of which are kind of fat at their own scale. And you want to say the smallest guy really dominates the count, and the ones that cross don't cost too much. And that takes 10 pages of pain, involving the words epsilon complexes. So yeah, I'm like, Howie, please, please take care of epsilon complexes. So yeah, that's all I'll say about the proof for now. OK, so quick digression to geometry of numbers. So geometry, all of this has been inspired for me by going back and reading papers from the 1950s about a different kind of moduli space. So remember we started with this flat torus, right? That was the first example. And we went in one direction, which was generalizing it to higher genus. But why not go the other direction and generalize it to higher dimensions? Look at flat tori of higher dimensions, or spaces of lattices. So here the main character is going to be a space xn, which is the space of flat tori, or the space of flat tori together with a direction, or or unimodular lattices, right? So I think of a coset GSLNZ, I identify it with simply the lattice GZN, or equivalently the torus Rn mod GZN. And I have actually two different transforms one can define. So if I start with f, which is a bounded compactly supported function on Rn, I can define, let's say, f twiddle of g. I'm going to write them as just g, and then they'll just be SLNZ invariant functions. I can define f twiddle of z to be the sum over all primitive vectors. Or maybe I'll do f twiddle to be all vectors. In Zn, f of g, all non-zero vectors. And then f hat, which is the closer analog to what we're looking at, to be the sum over all primitive vectors. So one's in my lattice. So people, of course, were interested in lattice point counting and averages. And so there are, if you go back and you look at the papers, so that there are 3 people, there's more people who are involved in this, of course, Minkowski, Hlavka, but in the middle part of this century, there are 3 people who are writing lots and lots of papers on this. All of the papers seem to have the title mean values on the space of lattices. In fact, the same person may write 6 papers with this title and say, refer to my previous paper. But what did Siegel show? And why did Veech attach the name of Siegel? Siegel showed that if you look at Haar measure on SLNR, you can look at the Haar probability measure on xn. So let mu_n be the Haar probability measure on xn. So scale it so it's a probability measure. What Siegel showed is that integral of f hat d mu_n, actually f twiddle is an easier statement. Integral of f twiddle is just the integral of f over Rn. This is not too surprising. What this is saying you take a random unimodular lattice, the number of lattice points in a set, the expected number of lattice points in a set is the measure of the set. Every flooring contractor knows this theorem, right? How many tiles do they need? If you tell them only the square footage, they're going to say, well, roughly this many, right? Like,
to point out to this concrete application of mathematics.
That's right. So I'm writing an introduction. I'm going to try to write a book about some of these things. And in it, I don't know if they'll actually ever let me get away with this. I write how Siegel came up with this formula after his earlier career as a flooring contractor. I do say the story is as like a little known story because it's entirely made up. So probably is not going to go in the final version of the book. But in addition, if you look at integral of f hat, this is a very pretty formula. You get 1 over zeta of n. Right, the proportion of primitive vectors is actually, it's a really nice way to define the zeta function. And you can use this to actually recover. So here I've normalized this to be a probability measure. Of course, there's a natural normalization here coming from the measure you build on this is exactly the same thing you do on the space of translation surfaces. You view this as sitting in Mn of R or in Rn squared. It's an area 1 hypersurface. You do the cone construction. If you fix that Lebesgue measure, then of course these things have intrinsic volumes. There's actually what you have to divide by to get a probability measure. And Siegel used these formulas to compute that. You get a product of zeta functions. But in particular, this tells you this counting. It tells you average counting. But then you can also look at integral of f twiddle squared or integral of f hat squared and ask what happens. And it turns out that for n bigger than or equal to 3, Rogers computed that integral, let me do f twiddle squared over xn, has a very nice form. It turns out to be the integral of f over Rn, quantity squared, plus a sum over pairs of relatively prime integers. So maybe I could, f integral over Rn, f of kx, f of qx, d Lebesgue of x. So it's a really explicit formula for the L2 norm. And I just want to say a word about how one gets it, because the last thing I want to do is I want to introduce a set of invariants. So this is the classical geometry of numbers formula for f twiddle, which is the sum over all. Rogers also claimed a formula for n equals 2, not for f twiddle, but for f hat. It's easy to check that f twiddle is not in L2 for n equals 2. Right? A ball of radius 1 can have lots and lots and lots of lattice points. If you just have a vector of length epsilon, and that set of lattices has measure epsilon squared. And that's bad for L2. F hat is bounded. F hat's in L infinity if you take the ball of radius 1. But Rogers claims a formula for integral f hat squared in n equals 2, which is actually incorrect. And so that's the joint work with Fairchild, is we've actually used work of Schmidt to correct Rogers' formula. But let me tell you just very quickly how Rogers got his formula and then where he went wrong. what he did is, and this is, wherever you see an n, you can also just put a 2 and you'll get what we want to do in the space of translation surfaces. Start with the function in BC of Rn cross Rn. Okay. Now define h hat by abusive notation of G to be the sum over all pairs of vectors in Zn prim, h of GV1, GV2. So this is, notice if I apply this to h of xy is equal to f of x, f of y, where f is in BC, this is exactly equal to f hat squared. Then h hat is exactly f hat squared. If h is this, you're just summing over all things. Now, if you can show that f hat's in L2 for any f in BC, then certainly h hat will be in L1 for any such h, because you can always dominate any h by an h of this form. Just take its max and times this larger of the two supports. So then h goes to the integral of h hat over xn is a SLNR invariant functional on Rn cross Rn, on BC of Rn cross Rn, right? So it has to come from integration against an SLNR invariant measure on Rn cross Rn. Now Rn cross Rn, for n at least 3, SLN acts transitively on pairs of linearly independent vectors. And that's a set of full measure. That's this term. This is Rn cross Rn linearly independent vectors. So really, if I were to do this with an integral of an h, it would be integral of h over Rn cross Rn. And I realize I'm switching between hat and twiddle, so there's some zeta functions that I'll need to pop in front here. And then this thing is the set of linearly dependent vectors. So if I have a pair of linearly dependent vectors, I can send it to any other pair with the same ratio. But since my vectors are in a lattice, their ratios are only rational. And so this is just indexing all possible rational ratios of vectors. And this is how you get this formula. And of course, you have to compute the constants. You have to compute the constants associated with these measures. But now I think you can probably see where Rogers might go wrong for n equals 2. For n equals 2, SL2 very much does not act transitively on pairs of vectors. Right? SL2 does not act transitively on 2 by 2 matrices. It preserves determinant. So if you do this for n equals 2, what you get is you can rewrite the integral. So the integral of h hat then, any SL2 invariant measure on R4, you can break it up into following pieces. There's an integral over R, where this R indicates what the determinant is. Once you fix the R minus 0, let's say, once you fix what the determinant is, you act transitively essentially on a copy of SL2. So, and that has one unique invariant measure, and you declare that once and for all. So here there's some measure on R, maybe call it d lambda. So this is over this is the SL2, which is the determinant equals t locus scaled. And then there's a part over linearly dependent guys, which you should think of as integrating over a copy of P1 of R, so the circle, of, again, now you have just a copy of R2 in here, which has a unique SL2 invariant measure. And there's this other measure, maybe I'll call it d eta of t on P1R. So maybe the takeaway point from this talk should be, now that we're in L2 for a stratum, let's suppose then there are these measures lambda and eta. Lambda is a measure on R, and eta is on P1R, associated to my to Masur-Veech measure on the stratum. More generally, if I can prove any other measure is in L2, the Siegel Veech transform, I'll get these measures. These are kind of measure versions of the Siegel Veech constants. So one of the uses of Siegel Veech constants is to detect different SL2 orbits and different SL2 invariant measures and orbit closures. This is a new family of invariants associated to SL2 orbits and invariant measures that, in fact, in some specific cases, we can compute what these measures are. So far, the ones we can compute are very special surfaces. They're essentially branched covers of what are called Veech surfaces. But I think one of the things one of the things is we have good computer programs to generate saddle connections for surfaces. One of the things you could do one of the things, the support of the measure lambda is essentially the collection of possible determinants of pairs of saddle connections, or as Smiley and Weiss call it, the area of virtual triangles on the surface, because they call pair of saddle connections, you look at the determinant. I think this could be a really interesting invariant to try and understand what possible SL2 invariant measures are. Of course, we need to compute some more to actually make this claim justified, but that's where we're going with this. Thank you.